spent 12 years at the Harvard-Smithsonian Center for Astrophysics in Cambridge, and then he moved to Rutgers in 1996. And he has been there since then. And today he's going to tell us about massive galactic clusters, and he's also giving a seminar tomorrow on cosmic supernova remnants.
Okay, yeah, that's all true. Thanks a lot, Doug, and thanks very much for inviting me. It's great to see some old colleagues who are now doing great new things here, and great to see so many new people. I really think this is a great attendance, and I thank everyone for coming. I'm going to talk today about some work on massive galaxy clusters. This is an example showing X-ray and some optical and infrared information. But first I'm going to go through a survey, a review of sort of cosmology, what galaxy clusters are and why we want to study them, how we study them, and then I'll end up with some recent results. So I'm sure many of you have seen this picture. It's a picture that describes the evolution of our universe. We have a Big Bang that occurred early on, and this image here shows you the first light that we see from the early universe. It's about 4,000 years. It occurs at the age of about 4,000 years. Then the universe goes through a bit of a dark phase, and then structure begins to form. And this envelope here sort of gives you a sense of how the scale factor of the universe has evolved. During inflation, it evolved very rapidly, and then it's evolved. It's continuing to evolve as the universe expands. And then you'll notice this upturn here, which represents the late onset of dark energy, the accelerated expansion of the universe, which was discovered in 1998 by two different teams of astronomers. So here I put some more numbers to this picture in what I call the timeline of the universe. And for those of you who are not astronomers, I'm going to just remind you that we talk a lot about the redshift of objects. Everything in the universe appears to be moving away from us, and we characterize that motion by looking at the ratio of the observed wavelength of emission lines or absorption lines to the emission wavelength. And we characterize that as 1 plus z. Z is the redshift. Now, the picture I showed you earlier, in which I sort of gave you a cartoon view of the size of the universe, also enters in here. So we can consider 1 plus z also to be the ratio of the size of the universe now to what it was in the past. Okay? So I'll use that redshift information throughout this talk. But here, I'll give you information on sort of what I mean by the different redshift values. So we're right here now, the current era, in which the universe seems to be dominated by galaxies. The universe has a temperature is defined by the radiation within it of about 2.7 Kelvin. And this is sort of the age of the universe now, 13.7 billion years, and we call this redshift 0. Now if we go back in time, so in this schematic down here or out here, if we go back a little bit in time, say we go back to an age when the universe is about 2 billion years old. That corresponds to a redshift of about 3. The temperature, the CMB radiation, was about 11 Kelvin. And that's when there's a peak number of quasars, which are very luminous objects that are believed to be in the center of galaxies and also evidence suggests they're supermassive accreting black holes. We go back a little bit further in time to when the universe was about 400 million years old. And that's the age when we believe the first stars formed. We don't have direct evidence for this. This is something that we're searching for in astronomy. The next big NASA mission, the James Webb Space Telescope, will hopefully be able to give us better evidence for the first stars and what their nature is. It's about a redshift of 10. Now, we can go back further. We enter what we consider to be the primordial fireball. And the fireball ends when the universe is about 380,000 years old. This is at a temperature of about 3,000 degrees Kelvin, a very important temperature. It's a temperature when atoms form. Prior to that time, electrons are free, and they can scatter the photons in the universe. It's like a fog. Only when that fog lifts when atoms form. Now the photons can freely stream and propagate to our telescopes, and we are able to then detect them, measure them, and learn about the properties of the early universe at this redshift, 1100. Okay, so that's sort of how the fireball ends. Going deeper into the epoch of the fireball, when the universe was about 24,000 years old, there was equal densities of matter and radiation. In the next slide, I'll tell you a little bit more about what I mean by these. And then going back a little further to when the universe was about 3 minutes old, 10 to the 9th Kelvin was the temperature. This is the period of time when the universe was hot enough that nucleosynthesis could occur. And that pattern of elements that come out of this nucleosynthesis process is a very distinct. It's only the light elements, hydrogen, helium, a little bit of lithium, and that's it. And we test the properties of the universe at this era by looking at the predictions of nucleosynthesis with measurements, astronomical measurements. So, in fact, all of these different pieces of evidence, all of these different epochs are supported to a greater or lesser extent with evidence. And what I'm going to talk about today a lot is the evidence we have on the properties of the cosmic microwave background. And then I'll talk a bit about what we learn about objects that are in between this region here, sort of this region here between the dark ages and today. So the energy density of the universe evolves with time, and that's what this picture shows here. I have, as a function of age, the matter density. Okay, I've equalized everything so that it's in terms of a mass density, kilograms per cubic meter. In blue, I show what matter does. As the universe is expanding, the matter density is obviously dropping, roughly like 1 over the scale factor of the universe cubed. Okay. The universe also contains radiation, and the radiation is shown in red, and the radiation density drops more rapidly than matter because the energy of the radiation is coupled to the scale of the universe, so it drops like 1 over the scale factor to the 4th power. And so that gives you the possibility to define different eras of the universe. There's an early era when radiation dominates, and that's up to about this period of time. And then afterwards, matter dominates. Okay? And that operates up until just about now, this is now, when we actually begin to see the effects of dark energy. And that's shown, the energy density of dark energy shown here as a cosmological constant is shown in green here. Okay? And so we are now in this era when dark energy actually dominates the energy density of the universe. And so numerically that's shown up here. Okay? So this is a pie chart of what the universe consists of. Radiation is completely negligible. I don't even put it on the pie chart. Dark energy accounts for about 72% of the energy density of the universe. Dark matter is about 23%. And then the remaining atoms, the stuff we're made of, is only about a little bit less than 5%. So this is the universe we live in. And it's interesting to note that the level of dark energy is very similar to the level of which the matter density is now, which has been falling very rapidly through the age of the universe so far. So a number of philosophically minded cosmologists are concerned about this apparent equality here. I won't go into that in detail here, but it's certainly an interesting issue to consider. So in terms of numbers, the matter density of the universe is about 1.5 hydrogen atoms per cubic meter. The number of photons is about 400 million photons per cubic meter. So there's a huge density of CMB photons in the universe now. And then this is just a numerical value for the equivalent matter density of the cosmological constant.
The amount of it grows when the universe grows.
Yeah, but the density remains constant.
The density remains constant.
If it's a cosmological constant. That is, of course, an assumption. And this is something that's being tested. But it's a very difficult thing to test what the variation of the dark energy equation of state is. But it's a prime focus of modern astronomical research. All right, any other questions? So I'm going to focus on a time of about 300,000 years. It's around here. Okay, it's about here. Okay, and that's when the temperature was 3,000 degrees, atoms formed, and the CMB radiation was able to freely stream.
When you say the temperature was 3,000 degrees, this is some kind of average temperature over the matter, or just can you talk about the temperature of free space, or what is?
It's the temperature of the photons and the matter. When they're tightly coupled, as they are in the early universe, their temperatures are in thermodynamic equilibrium, so they're equal. And in fact, as I'll show you, the universe as a whole emitted a very nearly black body type spectrum, which says that it was very close to thermal equilibrium. Okay, and so there's many other features of what happens during the evolution of the universe here. I haven't mentioned the pair production and annihilation of photons and particles at early eras. I haven't talked about the annihilation that leads to a matter excess rather than a nothing, right? If there was equal number of matter and antimatter, there should be nothing, but there's a matter excess. And that's one reason why we have a much different number of photons to atoms. But so there's many other things to discuss here.
I was wondering how you got the numbers, what those temperature numbers meant, really.
Okay, did I satisfy your question? Yeah, okay.
It's always very easy.
Yeah. All right, so I like to show this because the cosmic microwave background was discovered in my home state of New Jersey, not far from where Rutgers is, in 1965. This is the receiver that was used by Hughes and Wilson to discover this radiation. And a few years after that, NASA launched a satellite mission called COBE, which observed the sky over 4 years and made this map. Pretty boring. But that just indicates to you, this is just a display from 0 to 4 Kelvin. It indicates the extreme uniformity of the microwave background. Okay? So if you expand the scale here by a factor of 100, the color scale, you actually pick up a feature. This is a dipole feature, which comes about from the Earth's motion with respect to the cosmic microwave background frame. So it really gives us an absolute motion. If you can subtract that out and then enhance the scale by another factor of 100, you begin to pick out the galaxy, and this is emission from dust and electrons in the galaxy. But this emission out here, this pattern out here, are the variations in the temperature from place to place of the microwave background. So your question about the temperatures, from place to place, the temperatures varied by 1 part out of 100,000. So this is a different view of COBE, of the COBE map, and this is the kind of map that was generated by the WMAP satellite, which observed the whole sky at higher angular resolution and produced a finer map. So my colleagues at Princeton have been leaders at WMAP, and they're the people who have been involved in the work I've been doing on ACT, and they think in terms of the power spectrum. An average person looks at this, and or maybe the average physicist looks at this and says, well, I see some structure on there, okay? And what we want to do is characterize the scale of that structure, and so we take a power spectrum. In fact, we decompose this into spherical harmonics, and we plot the power as a function of the harmonic number, okay? And so we get this very distinctive and characteristic pattern of peaks in the power spectrum, the fluctuation spectrum of the intensity variations or the temperature variations. And so there's this strong peak at a multipole of 220, which corresponds to an angular scale about a degree. And that corresponds to a scale at which the universe has been fluctuating since the Big Bang and producing a large amount of power on this scale. Now, at about a factor of 2 higher than that, there's another peak, and another factor of 2 higher peak, and so on. And those of you who've studied music or have played a musical instrument might recognize this as sort of a pattern of a fundamental frequency and overtones associated with a vibrating column of air or a violin string or something like that. And in fact, what we are seeing here is a fluid that is undergoing similar types of vibrations. We are seeing acoustic vibrations of the early universe mapped out in the microwave background seen on the sky.
Such a high frequency.
I'm sorry?
At such a high frequency.
This one?
Yeah, no, the lowest one.
The lowest one?
It's already 220 or something like that, so that's not clear.
Well, this all gets down to the properties of the universe. How long has the wave had to grow? What is the speed of the wave? And all of that. And I can tell you that we have put together a model for the early universe that produces this red curve, and that agrees with all observations we have to date. There's 6 parameters for the.
What's the resonator then?
It's the universe. The universe itself is resonating. Okay. So what is the source? The original source of the.
Trying to get the scale out of something or another that existed to give it a fundamental frequency.
think it's the causal horizon.
Yeah, yeah.
Or sound
It's the
horizon.
maximum.
Sound horizon. It's the sound. Yes, it's exactly
All right, so sound wave going all the way across the universe.
right. And you're
Sound
getting.
wave travels at the point that electrons recombine with protons, and the protons then become can travel without any interference with their lives. So it's a snapshot, yeah.
Okay.
Any more questions for the speaker?
All right. So now I've talked about COBE, I've talked about WMAP, and there's a more recent satellite, Planck, which has got an even higher angular resolution to improve on the scale at which we can measure those fluctuations at higher scales. And so I'm involved in a project called ACT, which has angular resolution even better than Planck, in which we were able to not only detect the primary fluctuations of the CMB as shown here, but we're able to detect compact sources of astrophysical interest that are not primordial. They're things that are in the later universe, formed later. And that's what I'm going to talk about mostly next. Okay, so the Atacama Cosmology Telescope is shown here. It's a custom-built telescope that has a 6-meter diameter in here. Here's a list of a number of the institutions involved in it. And it has a camera that operates in the millimeter wave. The goal is to make measurements on arcsecond scales in the microwave background. That's 10 times better than WMAP and 5 times better than Planck. We proposed for this in 2000, and it was funded in 2003. Construction completed, this is the year about 2000, and so we've been surveying ever since. Okay, so the results I'll talk to you about today come from the first few years of the survey, but now we're running in polarization mode, and so we are able to, we're measuring now the polarization of the microwave background.
A question?
Yeah.
Before you get into the details of the construction. I was wondering what kind of questions you hope to be able to answer with this higher resolution that couldn't be answered with the existing resolution. What are some of the physics questions that you're heading towards? Or maybe they're not known yet.
No, there's a whole host of different projects that we have carried out over the years. So I'll try to get through to some of them in the lecture. And I have a few bonus slides at the end that I may be able to pop up to show you some of the things that we've done. Okay? But the drive has been for higher angular resolution.
The higher angular resolution will tell you what?
It will give you more information. It'll give you additional peaks out here. Okay? Although there isn't that much additional information, most of the additional information comes from the first three. There was a lot of concern about whether these peaks would be of similar height. And because they're of different height, it tells us something about how much dark matter there is in the universe. Okay? With higher angular resolution, though, we are able to study the point sources and the clusters. So that's my main interest, is to really focus on those objects. And from the distribution of clusters, we're able to get another projection or view into the cosmological parameters and constrain them in an independent way. Okay? So I'll try to satisfy your question as I go on through here. All right, so this is to prove that I was there. This was before we completed the ground screen. This is one of the highest permanently observed, permanently utilized telescopes in the world. It's at about 5,200 meters. So it's a very interesting place to visit. Here it is. This is a nearby volcano. The telescope's about a 45-minute drive from a nearby resort town, San Pedro de Atacama. It's up here. This is Chile, so this is the Santiago. And this whole area here is a very high, dry plain where there's many, many telescopes. And it's sort of the intersection here between Bolivia, Chile, and Argentina. And so here's a picture of ACT. Okay, so what were some of the highlights of what we were able to do with ACT? And so this is another view of that power spectrum, okay? And what it shows is these multiple patterns, peaks, acoustic fluctuations, and ACT is able to make measurements all the way down to the first peak and out to the 7th peak. So we, in fact, were the first group to publish the higher order peaks in the CMB. We were also the first group that was able to use these higher resolution maps in order to detect lensing of the CMB by the foreground large-scale structure. So that was one of the goals of our project, was to detect lensing of the CMB coming to us from a redshift of 1100. As those photons pass through all the intervening matter, they get distorted by gravitational lensing, and that imprints a non-Gaussian signature onto the map that we were able to detect. We now have a map of all of a map of the mass density, projected mass density of all the matter in the universe. And so that's been a very powerful tool that we've been using to compare to other astrophysical sources to understand about the biases of those sources with respect to the matter field. And then, as I mentioned, millimeter band point sources and galaxy clusters. And since about 2 years ago, we have polarimetric capability, ACT-Pol. And what is shown here is this power spectrum again. And this again up here is the power spectrum of the temperature. And what I like about this is if you look at the highest order multipole values, you see they reach this, this power law form. Okay? And that power law form is just due to the fluctuations due to individual point sources throughout the map. Those are radio sources, dusty galaxies that imprint their own fluctuation spectrum on here. Okay? So this just shows you this has to be removed in order for us to study the power spectrum of the primary CMB. But for people like me who are astrophysicists interested in studying the sources, this basically reveals just how rich this area is in terms of source properties. And then down here, this just shows the power spectrum of the E-mode polarization, again showing a number of peaks that are a little bit offset from the peaks of the temperature. Okay, so this was first published. This was our first paper from ACT-Pol. It was published just late last year.
So, do you have an explanation for this broad minimum?
This down here?
Yeah.
Well, a lot depends on how you mask point sources, because as you mask point sources, you can move this curve down a little bit, okay? But this curve has already been sort of optimally masked, okay? So all this is it's the intersection of the primary CMB and what the residual unremoved point source contribution is. Okay? And it turns out this is actually quite rich. This region in here, about a multipole of 3,000, is very rich. Okay? Because it doesn't just consist of point sources. It consists also of the clusters I'm going to be talking about now that are not point sources. They're a little bit resolved. Okay? And they come also correlated with each other. Okay? So there's a lot of potential information in this overlap region to learn about the unresolved source classes in the map. Okay? So we haven't tapped into that wealth yet, but that's something that's going to be happening over the next few years. Okay? We basically need to have a model that allows you to predict the shape of your source class in the power spectrum domain, and then see how well you can fit it in. Okay? So
this isn't stripe 82?
No, this region is not stripe 82. We're doing this in two regions that are south of stripe 82. We call them deep 5 and deep 6.
Where does the information come from on the point sources?
We can just mask them from the map itself.
Oh, you can identify them individually?
We just mask them
You're
from the
not
map
using
itself.
a PSS or anything?
For the CMB analysis, we use just the CMB data itself. Okay? And so we mask them, and we use them, in fact, to improve our pointing as a sort of a pointing check, pointing registration. All right, so that's sort of the CMB part of the talk. Now I want to talk about after the CMB is produced, and we still have this matter that's evolving and operating under the influence of gravity and expansion. Okay, and so we use the primary anisotropies in order to figure out what the initial conditions for that of the fluctuation spectrum of matter is. And we see that it's nearly scale invariant, Gaussian, primordial mass fluctuations. So we then take those fluctuations and evolve them under gravity using the general relativistic formulation for the expansion of the universe, including expansion, to then predict what the mass distribution of the universe is at any redshift, like for example now. And we then call that mass distribution the large-scale structure. And here's an example of a simulation from the Millennium team showing the distribution of matter after a long period of time when gravity's had the opportunity to act. We have void regions with not a lot of matter, dark here, and then the yellow regions are regions of high density that have collapsed to form the systems that I'm going to be talking about. The large, massive galaxy clusters tend to form in these interstices of merging filaments. And so the power of ACT and other CMB experiments like that is to allow us to make observations of the distant universe, that is to say at the CMB, as well as the nearby universe. And I've mentioned these things before, clusters and millimeter band sources. All right, so I'll just give you a quick run-through of a movie showing you how this is a simulation by a group at Max Planck, showing how pattern of fluctuations set down by the and constrained by the properties of the CMB under the action of gravity leads to the formation of a very rich, complex structure. Now, this calculation, and here's a redshift up here, this calculation is done at what's called co-moving coordinates. So in other words, I've taken out the expansion of the universe so that we're just looking at the same region of material and watching as it collapses into these regions where rich galaxies and clusters will form, and then voids where there's very little, there will be very little, a few galaxies. Okay, so the cosmological importance of the clusters is that they actually are signposts to these high-density regions that have collapsed under gravity. So they're the 3, 4, 5 n sigma fluctuations in the original primordial matter spectrum. We can see these objects to very large distances, redshifts of 1 or so. And because they're the most massive organized or gravitationally organized systems in the universe, they're very sensitive to the relative balance between gravity and expansion. And so, furthermore, we can calculate the number of clusters under what we know about gravity and the expansion. We can't really count the number of galaxies, but for clusters, we're actually in the regime in which we're able to make sensitive, fairly accurate calculations of their number distribution. And so the goal of observations is to try to measure the distribution, the number distribution, hopefully as a redshift, a function of redshift, and compare them to these predictions of the evolution of structure in the universe. So galaxy clusters are large organized systems. They have tens to thousands of galaxies, covering an astrophysicist unit of 25 cubic megaparsecs. For those of you who think in terms of, we astronomers think in terms of centimeters too, so I really apologize. I have no units for physicists here. But 10 to the 75 cubic centimeters is a pretty big number, right? Typical galaxy velocity, 100 to 1,000 kilometers per second. And I'm not even keeping CGS units. It's terrible. So in this particular case, when we measure the galaxies, we can measure individual galaxies' velocities, and we can get a whole collection of galaxies in a cluster and measure the dispersion of the velocities. And that then tells us gives us an insight into what the mass of the cluster is. So we can measure the cluster's mass from the velocity distribution. It's also true that a cluster is full of hot gas. As I said, 5% of the universe energy density now is in the form of baryons. A lot of that is in the form of gas. And in clusters, the gas falls into the gravitational potential well and heats up. It heats up to a temperature that's comparable to, in which the atom's velocities are comparable to the velocities of the galaxies. So that velocity turns out to be a temperature that corresponds to a temperature for the gas of millions to hundreds of millions of degrees. Okay? The mass of gas is actually quite significant. It's of order 10 times more than the mass of the galaxies themselves. And so we call them clusters of galaxies, but in some sense they're really more clusters of the clusters of gas. And the gas is not primordial. In other words, it's not purely hydrogen and helium. Yes, Gordon?
Is there a lot of gas and dark matter in the filaments as well?
Yeah, there isn't a separation between them. Though the separation occurs on the scale of galaxies, where there can be a separation between baryonic and dark matter components. But on larger scales, cluster scales and larger scales, we believe there isn't a very large dissociation between the components. So the gas is not primordial, which is really important. We see very strong iron lines from the X-ray emitting gas in these clusters, and that means the gas had to have been processed through stars. So a large volume of the universe then in these clusters filled with hot gas that's been processed through stars. So we can use the amount of gas and its temperature to determine the total mass of the cluster. Those of you who have studied stars know that hydrostatic equilibrium is an important feature of stars. We can use the equations of hydrostatic equilibrium to determine the mass distribution of clusters, under the assumption that clusters are in equilibrium, hydrostatic equilibrium. In the case of stars, that's a very good assumption. But in the case of clusters, the evidence is still out on how good an assumption that is. It's probably good to a factor of 2, maybe even good to 15-20%. But work is still going on how accurately we can determine the mass from the gas and the temperature. And so the final piece of information is probably the most important. If we look at the estimates of the mass we get from the velocity distribution and the estimates we get from the X-ray properties, we find that we require a much, much larger total quantity of matter. This is one of the evidences for dark matter in the universe, and the amount of dark matter is 10 times that of the baryonic matter, that is to say the galaxies or the gas. So in fact, these are really clusters of dark matter. We also know that most of the dark matter is not a normal type by combining various different pieces of evidence, and it's a type that is still yet unknown, one of the big problems in physics. And there we are, 10 to the 48 grams. 10 to the 15 times the mass of the sun. All right, so I'm going to show you some images of clusters. This is a very rich nearby cluster. It's the Coma cluster. It's in the constellation of Coma. This is the X-ray image. It shows the brightest X-ray intensity here in a false color display that indicates, and that falls off to lower intensity X-rays around here. Okay. The X-ray emission comes about from thermal Bremsstrahlung, and you may also note compact sources. These are unassociated with the cluster. They're likely supermassive accreting black holes, active galactic nuclei. So the X-ray emitting gas is this diffuse emission that fills the whole volume of the cluster. Now we can focus in on the center and look in there and see we have a beautiful set of galaxies in here. Right in the corner, in the center here, we have 2 bright, dominant elliptical galaxies. That's not usual. Usually there's 1 dominant galaxy, but Coma happens to have two dominant galaxies in it. And lots of other galaxies that are smaller that seem to be matched in color. Okay, so this is true color. This combines 3 different visible bands and put together so that it would be sort of the colors that you would see by your eye. And then this image here, now I've added in here the Planck image of the cluster. This is the image taken by the Planck satellite. Okay, and as you can see, it's very similar to the X-ray one, and in fact, these contours are of the X-ray data. And so the Planck signal is strongest right in the middle here, and then it falls off in a similar pattern to what happened in the X-ray. Okay, and the reason for that is simple. The process that gives rise to the signal we see in Planck depends on the properties of the gas, just like the X-ray emission we see from thermal Bremsstrahlung depends on the temperature and density of the gas. And that process, the underlying process that produces the signal we see here is called the Sunyaev-Zel'dovich effect, after the 2 creators. So the physics of the Sunyaev-Zel'dovich effect. So I'm going to go through, and I know I apologize, I'm not supposed to give any equations in colloquia, but These equations are easy. I have a bad one on the next equation, but bear with me. So the picture is this. You have a CMB photon that's propagating happily from the last scattering surface and interacts with the galaxy cluster, and it interacts with some of the hot electrons, and afterwards it has some of its properties are changed. Okay? So the physics process is the inverse Compton scatter, and we can write down fairly easily what the net energy change of a photon is in a Compton scatter. It is the ratio of the energy change to the original electron's energy, photon's energy, is just this combination of the photon energy and the temperature of the gas. Okay? So if the photon energy is much higher than 4 times kT, then the photon will lose energy. Okay? But if the gas is much hotter than the photons, then the photons will gain energy. Okay? And so since the electrons on the cluster are 10 million degrees, while the CMB photons are only a few Kelvin, we are definitely in the regime where photons will gain energy by interacting with the hot gas in the cluster. Okay? So the optical depth that's key for the scattering is just Thomson scattering. It's given by this, the number density of electrons, the Thomson cross-section, and the path length through the cluster. Okay? It turns out that product of these two is close to unity. And so the optical depth depends mainly on the number density of electrons, which is something like 10 to the minus 4. So this is a very small number. Okay? And then the other relevant parameter in this type of a process is the comptonization parameter, which is the integral of the electron temperature times the optical depth. All right, so here's the difficult part. How does one actually describe how the scattering process occurs? It very elegantly can be described in terms of the Comte-Nates equation. Describes how the photon field varies with energy and time. And so this is the original equation. We're in a regime where the number density is low, while this X factor, which is the ratio of photon energy to electron temperature, is very, this is a rather big, it's a rather small number. So this term dominates. We can drop these two terms, and we can, this is just a change in variables, it's trivial. And so we can actually then have an equation that we can solve. So this is the solution to the change in the spectral form of the CMB radiation due to inverse Compton scattering. It's a very simple, nice algebraic form. We can take the limit where we're in the Rayleigh-Jeans limit, and we find that the change intensity is given simply by minus 2 times y, the optical depth. Okay? So I show up here, this is a simple figure of the intensity versus frequency. The CMB is shown as a perfect black body here. Okay? And then this other figure here shows what this equation gives us. Okay? So it's just the effect of the Compton scattering, inverse Compton scattering of the photons. Okay? This effect has been highly magnified. The effect is much, much smaller. But what you can see is, in one regime, there's a reduction in the intensity. Okay? So this is where you'd expect a cluster to appear as a decrement, a hole in the CMB. Because the photons from this region have been boosted up in energy to this region. Okay? So then, on that side, at the high-frequency side, you have an increment tail. Okay? So there's a decrement, an increment, and right in between, there's a null. Okay? And so that's a very unusual and distinctive pattern of that is not usual in astrophysics, where sources tend to be either emitting or not emitting. They don't tend to be absorbing. Well, I mean, we have dust and we have other things that are absorption, but this is a source that will have an absorption at one frequency, a null, and then an emission. And so just to carry on with the pain of more equations, we can, if we look at if we apply a relativistic correction, we can actually see that the location of the zero does have some dependence on temperature, as does the maximum. The minimum seems to be fixed. So these are a couple of spectral forms. This is now the difference with respect to the CMB spectrum. We see in some frequency increment, some frequencies an increment, a decrement and increment, and it depends a little bit on the temperature. Okay.
Isn't there also a change in direction of the photons?
defocusing?
The photons will change in direction, sure, but they can be coming to the cluster from a range of different directions.
Yeah, so spoils the fine angular correlations.
Yes, so this signal is on a very compact scale, okay? It doesn't, it isn't, we do have to, I'll show you a map soon of what it looks like, but these are on arc-minute scales, okay? And they're fairly easy to recognize with respect to the fluctuations of the primary CMB. That was your question, right? Yeah.
Can you subtract them out from the cosmic ray background? I mean, it seems like it changes the temperature.
Well, they are so rare that they and they smooth you.
Doesn't bother.
Right. Okay, so this is actually very relevant. This is what Planck, the Planck satellite. This is some images of confirmed clusters in a range of frequency bands, showing over this range. These are the low frequency bands in blue, showing decrements. So these are actually fewer photons in the CMB here with respect to the local environment. This is at the null. So in fact, what you see here is just the primary fluctuations in the CMB, okay? And then at high frequency, the cluster appears as an increment, okay? So this is a beautiful demonstration of how, with multiple frequencies, you're actually able to pull out this signal. Okay, so when we designed ACT, we designed it in order to be able to measure the SZ effect and also do CMB work. And so we included a band in which we had a decrement detection of the SZ at about 150 gigahertz, a band where there was a no SZ signal, and then an increment signal out here. We also did some simulations to show sort of what the scale of a CMB on the CMB would be of the cluster. And what you see is the modeled background here is that Poisson signal of the point sources in the background. So it's a significant component. And so what we see here is a pattern of the cluster appearing as a small decrement at 145 gigahertz. There is a null. You don't see a signal. And then there's a brief, a modest increment. Okay, so that's sort of the level of detection that we're looking at. Okay, so take the red arrow away, and you realize how challenging it is to make these discoveries, to make these measurements. So I want to show you something else, which is shown here. So this is the mass function of clusters. So this is the mass of clusters over the range of 10 to the 14th to 10 to the 15th. And then this is just the number of clusters per square degree. And you see this falls extremely rapidly. Okay? So the very most massive clusters are extremely rare with respect to the lower mass clusters. Okay?
Are they really rare, or is it just you can't detect them?
No, they're rare. They're extremely rare. They turn out to be about 1 every 100 square degrees. They're just very rare. Because I showed you that simulation of structure formation, you only get the massive clusters at the most intense peaks, where the original primordial power spectrum had a larger fluctuation. And those are extremely rare. The Gaussian distribution, you're going to calculate a few sigma, those numbers get very, very small. Okay, so one last slide on motivating. As I mentioned, their clusters are very sensitive to the growth of structure, and we can set constraints on the cosmological model. The SZ effect is a scattering process, okay? So it only depends on the number of CMB photons, which is fixed once they start streaming freely, and the number of electrons that are in the cluster. So if you have a certain number of electrons and you put that cluster anywhere in the universe, it's going to have the same effect on scattering. So it doesn't matter where the cluster is, it should produce the same signal. As you bring it very close, it's going to span a larger region of the angular size, and so that will introduce a small difference. But once you get past a redshift of about 0.2 or so, 0.3, that angular variation is very small given our current cosmological model. So the rest, unlike other things whose brightness varies as 1 over the distance squared because of the inverse square law, the SZ effect is essentially redshift independent. The parameter that determines the strength of the SZ signal is very tightly correlated to the cluster mass, and that's what simulations have shown. And so we can have a very strong probe of the masses of clusters as a function of redshift by searching for clusters in the SE effect. So this just shows you a little bit of the work we have to do to find these clusters. So this is the original map, okay? This is a portion of the original ACT map, and showing the variations from the primordial power spectrum. And then superposed on here are two possible compact sources. One can filter out the CMB because we know what that spectrum is. We have the power spectrum. We have good simulations that tell us what it is, so we can filter it out. And when we filter it out, we can then enhance the signals from point sources, positive emission, and then clusters, negative emission. And so that's essentially how we do it. We do a match filtering and extraction. And clusters, of course, come in forms like this. The sources can be of two types. They can be just nearby radio galaxies or AGN, or they can be, nearby radio galaxies and AGN, or they can be more distant, dusty star-forming galaxies. But even with good maps, the clusters are buried in the CMB, as you can see there. But we can filter them out. We can filter the CMB out and get good detections of them. And so we're only looking at 148 gigahertz in this first study, and there the clusters appear of decrements. So in our first few years of observations, we came up with this sample of objects. These are the SC images from ACT. Again, all of them are decrements, and you can see more or less interesting structure. Not all of which is real. Some of this is just noise. Some of these guys have a bit of noise. And our job at Rutgers was to go out and to find the galaxies that are associated with each of them. And so I know you can't see this very well, but in each of these cases there's a very rich collection of galaxies that are the massive clusters that we associated with those SE decrements. Okay? No, these are ones that we acquired ourselves from SOAR and the Blanco formator in Chile. We over a course of about a season, we went and observed about 100 clusters, candidates, and came up with a sample of about 30. Our later work used Stripe 82, and there we had the wonderful Sloan data that we were able to do matching as well. So the other thing is, I mentioned the X-ray before. So to complete the cycle here, what I show is the X-ray fluxes of all of the cluster candidates that we confirmed optically. And I show on here that, and this is as a function of redshift, and I show on here what happens if you take a cluster that's 10 to the 15 solar masses, predict its X-ray emission, and see how that X-ray emission varies as you put it at different redshifts. So this is obviously the flux is changing because of the dimming, the luminosity dimming of the object. But what you can see is that our individual samples, our individual objects, fall pretty nicely around this 10 to the 15 solar mass line. And they're bracketed by, this is 4 times 10 to the 14. So this figure is to show you that the X-ray properties are consistent with the signal we're getting from the SC effect. And I want to focus on, how much time do I have?
Still just after 5, so about 10 minutes.
10 minutes? Okay, so I'll try to finish up quickly. So I want to focus on this particular cluster because it turns out to be one of the most interesting clusters in the universe. And I mean that, in the universe. It's the exceptional,
The known universe.
the observable universe. The known, you're absolutely right.
This universe.
The known universe, because we're still trying to push into the unknown. Okay, so it has this name, ACT 102, its coordinates, but we nicknamed it El Gordo.
I should get around to that.
Okay, good. You must have read my website. So anyway, this is the detection signal from the CMB from ACT. This shows an overlay of the X-ray contours on top of the optical. And it's a very rich and interesting system. We were able to get a lot of optical follow-up to get velocity redshift measurements of about 90 members. And we use that to determine the redshift, of course, and then the mass. And what got us very excited about this cluster was its similarity to the very well-known lower redshift cluster known as the Bullet cluster. And the Bullet cluster is famous because it seems to show evidence for the presence of dark matter that's independent of that truly a particle nature for dark matter. So the Bullet cluster consists of at least 2 components of galaxy galaxies, optical. There's a collection of galaxies here, a collection of galaxies here. And the X-ray emission, though, doesn't seem to line out perfectly with the galaxy distribution. So the X-ray emission has this bow shock here and this diffuse emission here. Now, what was possible to do with the bullet cluster was to use weak lensing of the background galaxies to infer what the gravitational mass of the cluster was, and that's shown in blue here. This is the result of a weak lensing analysis showing that where the mass of the cluster is actually associated with the galaxies. Okay, these two blue blobs here indicate where the dark matter is. And when you compare that to where most of the baryonic matter is, the red stuff is the baryonic matter, you can see that the dark matter and the baryonic matter are separated in space. Okay? So it's very, very difficult, perhaps impossible, for models that assume that the presence of dark matter is only a problem with our model of gravity. It's extremely difficult for those models to predict this kind of an offset between where the gas appears, the baryonic material, and where the dark matter appears as traced by weak lensing. And so this has been used to argue that the dark matter truly is some particle-based thing rather than a problem with our theory of gravity.
How do you know when you're looking at lensed energy versus emitted energy?
I'm not, well, I didn't go into gravitational lensing, okay? But basically what you're able to do is you look at many background galaxies, look at their orientation of their ellipticities, and average them. And lensing predicts that the average ellipticity should be sort of oriented around rings, okay? And so it's done independently of knowing where the gas is or anything else. It's purely based on the shapes of the galaxies. This has been, there are many techniques that have been, many years have been spent in developing techniques for doing this. We also, in the case of this cluster, we can add in strong lensing, which is the result of which produces multiple images of the same background galaxy and gives us even more precision to constrain where the dark matter distribution is, okay? So we're pretty confident that these combinations of weak and strong lensing are leading to a robust prediction of where the mass of the cluster really sits, okay? You should ask one of your astronomer colleagues who does work on strong lensing. All right, so we're interested in determining whether or not El Gordo seemed to be undergoing a violent merger. There were some indications in the galaxy distribution and the X-rays that it would. So we start with this original ACT map, in which we see the decrement, and then this is the distribution of galaxies. And if you analyze the distribution of galaxies that are color matched to what we expect El Gordo's galaxies to be, we actually find there's a peak of galaxies here and a second peak down here. And when we overlay the X-ray emission on it, we find a totally different pattern. We find that there's an offset peak of X-ray emission here, gas peak. And furthermore, there's an interesting wake in here. When we looked at this, we thought about it for a while, and then the hypothesis we came up with was that what we have is maybe a bullet-like component, like in the bullet, merging through the cluster, leaving a wake, and producing a gas peak here. And we're seeing the two components of the galaxies, the original two components that merged here and here. And so when we map the luminosity of the galaxies, or the number distribution of the galaxies, we find that we have this nice bimodal pattern. And that we tend to see a separation between where the gas is and where the galaxies are. And so we thought this was an interesting case of a merging system like the bullet cluster, but at much higher redshift. Oh, and the other thing is there's a feature here, a very long, thin feature that looks very much like a strongly lensed multiple image of a background galaxy. All right, so these are some of the details. So based on that work, it's the highest SE signal from ACT. It's the hottest cluster in terms of its X-ray temperature at a high redshift. It's the most massive and X-ray luminous cluster above this redshift. From these velocities, we're able to get a dynamical mass. From the Chandra data, the X-ray data, we're able to get a mass as well. and we see this separation between the hot gas and the galaxies.
There ongoing effort for weak lensing measurement.
Yes. So I just want to go, yes,
So Rosat was all sky, wasn't it?
yes.
So why was this not discovered previously in the X-ray all sky images? Because there's quite a few clusters with redshift 0.8, 0.9.
This is the Rosat emission from El Gordo. And it's above the line that corresponds to what should have been a bright source in the Rosat all sky. So for whatever reason, I didn't believe this X-ray measurement. I thought there might have been some contaminating X-ray emission or something else. So when I proposed the Chandra observation, I assumed the cluster was here or here. And so I proposed for a much deeper observation than I needed to just to detect it. And so when I did detect, luckily we got all these photons. We were able to do a lot more with the observation that we got. But the point is, this just was missed. There was no follow-up procedure to find this cluster. And it's partially because it's a high enough redshift that it required deeper imaging. We needed to go and image it 2 or 3 times to be confident. So it really was detected well by Rosat. Okay, so it's the mass of the cluster that really matters. So I want to go into some detail about how we weighed El Gordo. So the first thing we did was we used the velocity dispersion, which is about 1,300 kilometers per second. And we used scaling laws with respect to simulations from Gus Everard's work. And we get a mass of about 2 times 10 to the 15th solar masses. We then use the X-ray properties, specifically how hot the temperature is and how much gas mass there is. And that then gives us an X-ray mass, which is about 3 10 to the 15. And then we were able to use scaling laws that my former grad student developed relating to the strength of the SC signal to get us a mass estimate from the SC, from the original act detection of, again, about 2 10 to the 15. If we put all these numbers together, we get a value of about 2 with an error bar times 10 to the 15. And we compared to all the other sources that we knew, all the other clusters at high redshift, and this one is the most exceptional by about a factor of 2. More recently, we actually did weak lensing of El Gordo. And so this is the pattern of weak lensing observations we had. There was a set of observations that we took, and then another team took a set of observations. We put it all together. And this is what we get for the mass distribution of El Gordo. We have these 2 clear peaks in the mass. It's very much like the bullet cluster. And when we overlay it with the luminosity from the galaxies, we again find, just like the bullet cluster, very good agreement between where the dark matter is and where the galaxy luminosity is. And when we overlay it with the X-ray, we get something that's quite different from, it's different from the bullet. There's a little bit of an offset of the weak lensing with respect to the gas core, and there's actually no gas peak up here. In any event, I don't have time to go into the details of that. What I do want to get into is that the weak lensing observation measurement confirms the mass to be 3 10 to the 15 solar masses. So why is that interesting? Well, one of the questions one can ask is there a cluster that's just too big to exist? You know, there are no banks that are too big to exist. Our federal government tells us that. But perhaps there's a cluster that's just too big to have formed in the length of time it had for gravity to collapse and grow it. And so there are a number of groups that have looked into this possibility. And so here's an example of one by Mortensen et al., in which we've put El Gordo on here. So for that, you need to know what the mass of your cluster is, and you need to know the redshift, and then you need to know how much of the sky area you've surveyed. Okay, so in this particular curve, this says this is the survey the area we surveyed with ACT itself. Okay, this might be a better curve. This is the area that ACT and SPT surveyed together. So they're both, and they both detected El Gordo. So if you look at that, you see that at high redshift, a lower mass cluster is more unlikely, whereas at low redshift, a higher mass cluster, it has to be higher mass. And that's just because structure grows, right? So this curve just indicates the growth of structure. And at the time we got the original measurements, we put El Gordo here, and it was essentially pretty much consistent with the area that we saw. A very rare event, but not something that would be inconsistent with the current paradigm for the evolution of the universe. And so now if we put in our new weak lensing result, that then bumps us up to here and puts us into a regime where it's somewhat more uncomfortable. Okay? Now, I would not argue that we should throw lambda CDM away because one cluster happens to be falling in a particular spot of parameter space. But in any event, it says that this issue of whether a cluster is too big to exist in the universe is something that has some merit to explore.
And the weak lensing mass, if it looked like it could be a merger of two events, is it? Sorry, is it the weak lensing mass centered on the larger of the two, or?
We went into some great detail on that. So the question is, depending on what your whether you put the two. So when you do the weak lensing measurement, of course, you don't know where in the line of sight those mass components could be. Okay, and so we assumed various assumptions about whether or not what the offset out of the plane of the sky for both of these components is. Okay, and so only when the offset gets quite unusual do you get two independent clusters. We assumed it was one cluster with two components, and that gives us that total mass. Okay, and unless it's a very unusual configuration, we have constraints from the velocity distribution that tells us they really have to be close to the plane of the sky, and also the X-ray emission tells us that as well. So they can't be very far out of the plane of the sky, in which case we then calculate R200 from integrating everything, assuming the proper angles. Okay?
I'm just saying, a theorist would just simply say, that's two clusters divided by 2.
Right, but that theorist would have to show me in a simulation where he has two 10 to the 15 solar mass clusters merging, and no simulations show that. So it's still an unusual system. But I am not claiming that it falsifies lambda CDM. Okay, there are assumptions in this Mortensen curve that are not conservative enough, and so in fact I would say these curves should move up by a factor of a few. Okay, so I don't want anyone to take away a message that we're falsifying lambda CDM based on this one cluster. I'm just pointing out how it's an interesting question. All right, and so the interesting question, which we've actually submitted a number of proposals with this title, is El Gordo the fattest cluster in the universe. This has motivated our search for clusters of exceptional mass and high redshift using the available Planck data. So we found El Gordo in only 1,000 square degrees. The sky has about 40,000 square degrees. So how likely is it that we found the most extreme, most unlikely, most unusual cluster in the sky in only looking at about 7% of the sky? This is a map of the unconfirmed Planck clusters from 2013. Okay, there's about 350 objects here. This shows all of the confirmed Planck clusters in black here as a function of redshift versus mass. And out here at high redshift, high mass, there's only two, and El Gordo is the most massive, according to Planck. Good, they agree with us. So the question is, where do any of these clusters that are unconfirmed fall in this regime? And since Rosat missed El Gordo, it's not unlikely that the follow-up hasn't been sufficient on these guys in order to find the most extreme clusters. And so we started an observing campaign in which we had 20 observing nights last year, all of 2014. And so we found a large number of candidates. In fact, I looked at the Swift X-ray telescope and found about a dozen confirmations there. And this just shows one of our optical near-IR confirmations. This is the color magnitude diagram. This is the magnitude versus a matched color. This is for the cluster sequence. And there's a couple of BCGs here. Lots of reddish galaxies throughout here. So we're working on this. We have velocity measurements of the galaxies in there. We're also planning for the next upgrade to ACT, which is an advanced ACT poll, in which we're going to survey 20,000 degrees of the southern sky. Okay, so this is just showing other surveys and where we plan to survey with ACT. In that survey, we're going to do CMB measurements. We're going to try to measure the tensor to scalar ratio, the R value. And we're also going to measure and detect a large number of dusty star-forming galaxies and a very large number of SC clusters, maybe 20,000 clusters and 10,000 high-significance dusty star-forming galaxies. So that's work that's going to be going on through the next few years, and it's going to be a lot of work, but it should be a lot of fun. So here's my summary. El Gordo remains at the top of the heap in terms of massive high redshift clusters, and our recent Hubble weak lensing just confirms its high mass. We are extending our search to extreme clusters to the All-Sky Planck survey. We've already found a couple of dozen new clusters to characterize. And with advanced ACPOL, we'll carry on an even more sensitive survey for clusters, millimeter sources, and CMB work in the southern sky in the next few years. So I've had a number of talented people work with me on ACT, current grad student and undergrad, and then a number of recent alumni from my good colleague, postdoc Felipe, my former student Nalima, a great Chilean grad student who's now at Leiden doing a PhD, and then a number of very talented undergrads who I was very happy to work with. And finally, the Atacama Cosmology Telescope is a big team project. This is the list of people who are on the El Gordo study. I want to remind everyone that Lyman Page is the PI of the project, and he's been the real guiding force behind it, as well as other people like, let's see, where is David Spergel. So we've been funded by the NSF and NASA, and hopefully I can come back at some point in the future when we have advanced ACPOL results and tell you about them. Thank you.
Well, we had a lot of questions during the colloquium, but we can take a few more.